All right, so I'm going to just turn this way because I have an audience here. So, welcome to the very first session of Shadow the Scientist for 2026. My name is Jamika Marshall, and I am very pleased to serve as the Shadow the Scientist Programs Manager. Tonight, we are going to be joining the amazing Gemini Science Operations team in two hemispheres. Gemini North here with Brian Lameau and Emily Peavy. And then we have our amazing guest that we will actually be shadowing, and that's Lindsay and Pablo of Gemini South. So let's take it over to Brian and Emily.
Aloha, Jamika. Thank you so much for setting this all up. Thank you to your family for joining us.
Yeah.
So as Jamika mentioned, I'm Brian. I'm a staff scientist here at Gemini North. Emily, you want to introduce yourself?
Aloha, everyone. I'm Emily Peavy. I'm the Senior Education Engagement Assistant here at Gemini North Telescope as part of NSF's NORLAB. And it's so nice being inside, not in the middle of all of the very, very heavy rain that we've gotten in the past couple of days. Jamika mentioned we do get snow here in Hawaii at the summits, including on the Mauna Kea summit. And we get those during this time of the year when it's our rainy, wet season. We get these Kona low big thunderstorms. And we had a really, really big one pass through yesterday, the past couple of days, and that dropped a lot of snow for us here.
Yeah. Yeah, so just to orient everybody, it's like this is worldwide astronomy right now.
Yeah.
Two hemispheres.
Yes,
time of 7 hours. You guys are 3 hours off. It's cloudy there. It's snowy here. So we're in Hilo. We're at our base facility at Gemini North. This is where we operate the telescope from. We don't operate from the summit facility near the summit of Mauna Kea. We do most of it from basically sea level. Here we're about 40 kilometers away or so from the summit. And we interact with the telescope through fiber optics. And so actually our night, so we're at 4:10 right now. Our night's going to start in a couple hours. And despite the snow and the crazy weather and everything, we just got the call from our acting head of science operations that it's game on for tonight at Gemini North.
What? Really?
Here is a live picture of the summit of Mauna Kea. This is a public page. Anybody can go on this page and take a look at our status. So on this status page, we have tons of information. It's useful for us at nighttime when we wake up in the middle of the night and try to wonder what's going on with the telescope, or what's going on at the summit of Mauna Kea. There's all sorts of weather information here. We have information for scientists that engage with the observatory about whether or not they can use the telescope this evening. And this is what the summit looks like right now. So you can see, first of all, yes, there is snow in Hawaii. And it's a little bit unstable up there. So this is our up cloud camera. This is all mounted on the structure around the Gemini telescope. And this is looking directly up. And you can see blue sky sometimes, and then the big cloud hits it. So yeah, we would not be open right now if it were nighttime, but we'd be sitting around waiting to see if we could open. But we have a sister telescope in the south, and so I'm going to go to that page. So this is also a public page, and we've now transported from the summit of Mauna Kea on the Big Island of Hawaii to Cerro Pachón in Chile, and just recently they updated their status page with these kind of like 15-minute frames from their equivalent cameras. And you can see it's a little bit different weather there.
So let me just pause and say we have people going, oh, wow, you can see the Milky Way. Because it is, a little cloudy here in Phoenix, but it is gorgeous there. Absolutely beautiful. So what are we seeing? There's a few lights. What town or city is down there, Brian or Emily?
I'm going to pass that to Lindsay and Pablo because they know the area much better than I do. I'm assuming it's not.
There's a few. The really bright one That is La Serena and Coquimbo, where we're observing from, basically, in the base facility. The other lesser lights, I think, are Ovalle and Vicuña.
And Andacollo.
Oh, and Decoyo as well, yes, you're right. And yeah, it's very, very noticeable, the light pollution from it. And we are working on like mitigation efforts to try to get the light pollution down. We've recently come to an agreement. Some nearby stadiums have changed their lighting. So it now doesn't have any light sort of going up from them, and it's made a noticeable difference in it. But as you can see, still work to do.
Well,
Yeah, it reminds me of Palomar actually. Like when you could see Temecula there off in the distance, and also Lick Observatory when you could see San Jose off in the distance. We don't have an equivalent here on the Big Island, but yeah, it's definitely noticeable.
In the South Cloud camera, is that a satellite that we see keep passing through?
Yes, it could be planes. We're right on the direct route down. If you're coming from the United States and you're flying to Santiago, you pass directly overhead on the observatory. So we do get a lot of planes on that route. So that's what a lot of those probably are.
Oh,
Yeah, luckily we don't have that same problem here, because otherwise we'd have to have laser spotters still, and that would be, well, it would be science fellows and they'd be out there in this weather.
oh no. Yes, we were just so we have a great crowd here, and so we had a question about La Serena. Is that where the nearest university is?
Yes, there's a university literally next door to the base facility here. I could walk there in 5 minutes right now.
Oh wow. Okay, so one of our audience members was just commenting that here at the American Astronomical Society winter meeting in Phoenix, where we all are, some participants from that university. So that was why we had that question. Thank you so much, Lindsay, and welcome, Pablo. I apologize for not introducing you both. Lindsay and Pablo are who we are shadowing tonight as they run the telescope at Gemini South and on Cerro Pachón in Chile. All right, Brian, back to you. What will we be seeing with Lindsay and Pablo this evening?
Yeah, so just to contextualize again for everybody. So Lindsay and Pablo are staff scientists at Gemini South. They're in La Serena at the base facility. So like us, we observe from Hilo on the east side of the Big Island, about 40 kilometers away from our telescope, although we can drive up there. We have staff that drive up there every day. And we can drive up there at night if we really need to. Basically, same. So our sister telescope, Gemini South, Lindsay and Pablo are observing from La Serena, and they're about 40 kilometers away from their telescope on Cerro Pachón. Is that all right, Lindsay, roughly? But you guys, it takes a lot longer for you guys to drive up there than it does for us. I think isn't it about 2 hours to get up there?
It's like an hour and 45 minutes. It can be 2 hours if there's a lot of traffic.
Yeah. So yeah, hopefully middle of the night something goes wrong. You don't have to drive up there. And so we always have 2 staff on duty at nighttime. It's roughly 11:15 p.m. in Chile, so it's the middle of their night. It's summer, not winter. And we have 2 staff on duty. Lindsay tonight is the observer, so Lindsay has the scientific roadmap for tonight. She has all the plans. So Gemini Observatory works on a queue system. We have scientists from all over the world propose for telescope time on the north and the south. About 10 to 15% of that time is awarded. And then there's a huge number of plans on any given night. A staff member called a queue coordinator puts all those plans together for every single different weather variant, so anything that could possibly happen on that night. And then gives all those plans to Lindsay, and Lindsay then uses those plans to make a roadmap of the science for the night. Pablo, on the other hand, is the operator. So he is the kind of conduit between the night operations and the rest of the observatory. So if something goes wrong with the observatory, Pablo would be calling other staff members. If somebody needed to go up at night, Pablo would be the person to trigger that. Pablo also moves the telescope. So anytime Lindsay wants to move to a new observation tonight, there's relatively long observations. So there'll be like an hour in between observations. But once
we will be starting in about 30 seconds.
Oh yeah, okay.
Oh, is there a question in the crowd with Jamaica?
Yes. Sorry, we do have a question. We have a lovely, lively crowd here. So the question is, why are these called cloud cameras?
Okay. So these are super light sensitive cameras. This is for us, I mean, for a variety of reasons, but to see whether there's cirrus in the sky, so thin cirrus, we have to, it's especially like the observer's job, so Lindsay tonight, to assess the weather conditions. So a scientist would propose for a certain observation, and they would say, I need absolutely cloudless skies to be able to see the super, super faint target that I want to see, a super faint galaxy at the edge of the universe. So I need the best possible
13.5, please, Pablo.
the best possible conditions for that. And so at nighttime, we have quantitative measures as well, but we would look at these cloud cameras and we would assess, is there any chance of any like light cirrus? If so, let's wait for another night and we do some other observation.
So these cameras are not the cameras that we're using to collect the scientific data.
Right.
These cameras are just for us to be monitoring the weather systems that's around and monitoring for clouds.
Right. And so we have all these like quantitative measures up here. You can see a radar image up here. But cloud cover is a kind of tough one. It's not one that you can easily measure. And so the human eye the trained human eye is pretty good at detecting clouds. And so that would be kind of like our first line of defense for trying to understand what the conditions are for that night. We have other sets of conditions that we pay attention to as well.
Thank you so much. That was the perfect explanation, you all. Emily, Brian, Lindsay, Pablo, thank you so much.
So they're actually moving the telescope right now. So they just finished up a observation on one target, and then they're moving to the next target for the night. And they're also switching instruments. So I'm going to bring up a mirror of their screen in a second. Okay, so here we are. This is the live Gemini South. This is Lindsay's screen. So, and it's in fact one of 6 screens that Lindsay has. So it's going to be a little bit weird moving around here because I actually have to scroll. Let's see if we'll go here. Okay,
Bottom right is probably, well, there's top center gives you the telescope status display. Bottom right is where I have the ghost ISD for when we're doing the vision.
Perfect. Awesome. Thanks, Lindsay. Okay, so this is this screen here is called the telescope status display. It contains basically all the top level information that we need to understand where we're pointing and where the telescope is pointing, and some other information that helps us, well, technical information that helps us assess what we're doing and whether or not we're focused well and in the right location and pointing to the right instrument. So Gemini, both Geminis are very agile telescopes. They are equipped with 4 instruments at any given time, at least. And so this, yeah, my cursor is visible. Okay, this is a top level rendering of Gemini South. East and west are labeled here. This black area is the shutter of the telescope. And then the circle is where the primary mirror is. So basically where the telescope is pointing. So we're pointed almost straight up here, and maybe like 60 degrees elevation. And then this is a side level rendering of the light path of the astronomical object that's being observed. So the light comes in, hits the primary mirror, hits the secondary mirror, goes through a hole in the primary mirror and goes into this instrument cage down here, instrument support structure. And so you can see that there's numbers here. Maybe you can see on the screen, 1, 2, 3, 4, 5. Effectively, each one of these is a different instrument. So telescope is a light bucket, telescope collects, gives it to the instruments, and the instruments say, okay, got it, thanks for all that light. I know what to do with this now. And so we have GMOS is our most popular instrument, and this is actually mirrored on both, this instrument is mirrored on both telescopes. It's an optical imager spectrograph and integral field unit spectrograph. So it can take images of the sky in like 25 different colors, so roughly 25 different bands. It can take slit spectrograph observations, so single source, disperses the source, and observations all the way from like bluer than the human eye can see all the way to redder than the human eye can see. It can do multi-object spectrograph, so you can take observations of up to like 50 galaxies at a time, or 50 objects at a time, 50 stars at a time. Or you can take an integral field unit spectral image, which means you get a spectrum of every single point on the sky where it's pointed. So we just finished that up. Probably the data are still there somewhere.
Sorry, I've been doing the acquisition and I lost track of what you were saying.
Okay.
Oh, there you go.
This is coming
Yes, so right now I'm doing the acquisition. And we have 2 IFUs, and we're just lining them up on the target and making sure they're nicely centered. And they're pretty much ready to go, and they're not saturating anymore.
Yay!
So I'm going to start the science.
Awesome. Yeah, so this is like no, sorry, go ahead, Lindsay.
No, go ahead. I'm just writing down the night log.
Okay. Yeah, this is like one of the awesome things of Gemini. It's super fast. Like I can't even keep up. Like the slew time to move to a completely different part of the sky, a completely different instrument. So we have a tertiary mirror in here called a science fold, and that redirects the light. So it redirected the light to port 3 previously for GMOS, and then we have our Gemini calibration environment here in port 2. So it actually flips around when we want to take calibrations right after we take the science observations. It flips around and illuminates. We illuminate our Gemini calibration environment, and it shoots calibration photons into GMOS. And then our tertiary mirror science fold moved out of the way and let the light access this GOES instrument here. So this is a bottom port instrument. So basically, we're just passing the light right down to the bottom. So this entire process, moving to a completely different part of the sky, this hundreds of tons of telescope and dome structure, these kind of like 2-ton instruments, rotating everything around on our CAS rotator, repiping the light from one instrument to another instrument. That whole process is like less than 5 minutes. We put 6 minutes just to be generous, but it's usually like 4 to 5 minutes. That's absolutely amazing. So as Lindsay mentioned, we've now moved on to this GOES instrument. This is a very high resolution spectrograph. This is usually used for stars in the Milky Way, though it can be used for very distant, like really active black holes, other really bright astronomical phenomenon. And it's an integral field unit spectrograph. So again, it has the ability to take a spectrum of every point in the sky where it's pointed. It has 2 different IFUs. I think for GOES, the 2 IFU method, it's using, is one of them pointed at sky? Is that right?
You can either have one pointed on science and one pointed at sky, or you can have two pointed at two different objects, which is what is happening now. If you go
Okay.
back to the bottom right, I'm looking at the slit viewing camera now, and you can see both of them have objects in them.
There we go. Oh yeah, let's watch that.
So that's actually the quick look of the data that comes out, but that's old data from the last thing we're doing. These are 15-minute spectra. If you go down, so on the bottom right, we're looking through the slit viewing camera, and you can see there's a series of like 7 fibers, and you see the object in the middle in each of them really brightly. And you can even see like a nice, that the seeing is very good because it's very, like you can see it's not taking up that whole fiber. You can even see the edges of it. So we're having really nice seeing. And then
So
you
you
can
have
see
a-
like the sky slit, there's nothing in it.
Yeah, so the slit viewing camera, so we actually don't have this instrument in the north, so I'm not as familiar with it. So
Yeah.
I'm very happy for you to lead us through this, Lindsay. But just like Igrans 2 in the north, you have a full width half max measure there. So it says right in the middle, it might be too small for people to see, but full width half max, IFU blue, IFU1 red, IFU2 blue, all measuring around 0.6, actually, and improving. So you're monitoring the source in real time. You're able to measure the full width half max. At the same time, you're getting the light from the source and piping that through an integral field unit spectrograph and getting a spectrum. So this is a measure of the basically turbulence in the atmosphere and on the ground. It's the twinkling of the stars, and they're getting about 0.6 arc second seeing. So it's measured in which band, Lindsay? B?
Roughly? So it goes basically G, R, G, R, G, R.
Yeah.
And the top 4 are what we're using now, standard resolution. And then the bottom 2 are high resolution, but we're not using that at the moment. So
okay.
That's
okay,
why
so,
those values are themselves.
But yeah, G band seeing of 0.63 is pretty dang good. So you're like creeping into IQ20 here, the 20th percentile best seeing from probably your like 30th percentile best seeing from Cerro Pachón. So very nice night, cloudless, wonderful seeing, no technical issues so far.
Do we know what type of object we're observing right now?
So they're looking at star formation in a nebula.
Which
Or I
program?
guess it's FT113. So it's a fast turnaround program.
Oh, okay.
I'll take a look. But yeah, so yeah, we have this awesome, for those that AAS that propose for telescope time, we have this awesome way of proposing for telescope time at Gemini North and Gemini South called fast turnaround. So if you are affiliated with the US institution or Canadian institution or several other institutions around the world, you can apply for time. It's every month. You said it's 113?
Yeah.
Okay, cool. So every month you get a chance to apply for time. The proposals are due at the last day of the previous month. And then you get the honor of peer reviewing everybody's proposal, all your competitors, and learning about tons of cool science. And then if you make it through, it's about a 30 to 40% success rate. So not too bad. Apply 3 times and you for sure get it. That's how statistics works. And then you can get your data within like, we've gotten PI's data in like 3 days. So the like canonical amount of time is better than 3 months, but a lot of times we get it within the like first couple weeks. So from the time you propose until the time you get data can be as short as like 3 weeks. And in astronomy, that is extremely fast. I'm used to waiting like 6 months or 8 months to get my data. Yeah, so these are two probably massive stars that are being pointed at right now. This particular program is looking at the star formation history of a nebula. And so by looking at the distribution of like the masses, the colors, and the properties of the stars in a given star forming region, you can tell a little bit about so certain like high mass stars only live for 10 million years only. And so if there are some around or there are a lot around, that means the last major star formation event was less than 10 million years ago, by definition. And you can also, by pointing an integral field unit like this and getting high resolution spectroscopy, you can tell stuff about the surface gravity of those stars. You can tell stuff about like whether there's material outflowing from those stars. You can get the kind of evolutionary phase of the stars that are being targeted, and that can give you some information on what the environment of the stars are, how they feed back with their companions, again, where they are in, like, let's say you see a very massive star, where they are in their 10 million year life cycle. So are they at the very end? Are they just beginning? Sometimes people look for like protoplanetary disks, so for exoplanets being formed around these stars, though probably not massive stars.
I was gonna say, we don't typically. A kid just asked me that the other day. Do we often see exoplanets forming around massive stars? And my answer was no. We don't typically, not around massive stars.
They just don't live for that long. And the radiation is just way too much to keep the debris disk. So yeah, typically, as far as I know, it's not really my scientific area of expertise, but A stars are kind of the most massive stars where those disks are seen on a regular basis, and those live for 1 to 3 billion years, roughly. So our solar system, I don't know, probably would have been destroyed, but we're at 4.5.
Oh yeah, we're a nice medium-sized star.
Yeah, we're Goldilocks.
Everything about everything with the Earth is medium. We are nice. We're orbiting around a medium-sized star in a medium galaxy.
Nice and comfortable, nice and easy. And Lindsay, the data that come out are on the quick look on 3, and this is stale data, or this is data that just came out?
This is data from the first thing we did tonight, but it isn't data for this newest observation. So you can see here the
activity bar
on the quick look. You see there's like a blue bar going across.
Yep.
That tells you how much time there's left. So there's a little under 5 minutes left, and then you'll see the new data coming out.
So you do about 15-minute exposures.
Yeah, we have 3 15-minute exposures. We're still on the first one. You'll also notice that the time on the sec-exec is very different. Ignore the time on the sec-exec. There's like a 400 odd second fudge factor there, so it's just
really?
it tells ones. Yeah.
That's funny.
For everybody joining us, feel free to jump in with any questions if you have anything.
Yeah, please. Also in the room, if you guys have any questions. Welcome. Or anybody online, you're welcome to put questions in the chat or raise your hand. So yeah, I was just looking at this program, and so the brightness of the objects that they're targeting here is V-band 13th magnitude. So the human eye, if you have like really, really good eyesight, you can see about as faint as 6th magnitude. So we have lots of like really weird, silly measurements in astronomy. Magnitude is definitely one of them. I'm used to it now, so I don't remember how crazy it is, but it's
the lower the number, the brighter it is.
The lower the number, the brighter it is, and change in magnitude of 2.5. So if you change the magnitude by 2.5, that changes the brightness by a factor of 10.
It's a really dumb.
It's a really
history
weird system. It's a logarithmic system, and it has a negative sign in front of it inexplicably. So like the sun, apparent magnitude is like minus 25.
Yeah.
So it's like super, super bright. It tracks, right? Sun's super bright. Yeah. So this set of stars is 13 magnitude.
So you wouldn't see it to the naked eye. So that's an important thing. So we were just talking about how this is probably a very, very massive star. And the rule of thumb is that the more massive the star is, the more energy that the star needs to create in order for the star to counteract the mass, for the star to be in balance. So for this being a very massive star, this is also a star that would be very, very bright. However, if this star is also at 13 magnitude and is very faint to our eyes, then that is a star that's also very, very far away. Because that's one of the biggest challenges of astronomy is distance. If something is very, very bright and very far away, it can still be very, very faint to us.
Right. Yeah. So this would be, more than 10 trillion times fainter, apparently, than the sun.
Yeah.
But it's so for us, it would be like about 1,000 times fainter than we could see with the naked eye. And this is actually looking in the constellation Orion.
It is.
Yeah.
So I was trying to calculate that in my brain when they said star forming region, because of course one of the most famous star forming regions is in Orion. And I was going like, oh, would Orion be close to the center of the sky almost at midnight in Chile? And I'm like, it might be, but I don't want to be that confident, sort of thing. But with that, I wouldn't have thought it was in Orion, because Orion's not that far away from us. Orion Nebula, but maybe somewhere else in the complex.
Right, it's somewhere else. I don't think it's directly at the M42, right?
Yeah, it's not in the famous Orion Nebula. It's in the larger Orion star forming complex.
Yeah, but for those that know Orion, like Rigel and Betelgeuse, those are like second magnitude. I don't know exactly, but something like that. So yeah, like pretty bright, easy for us to see on a clear night. Yeah. So these are 10,000 times fainter than that.
So much farther away.
Yeah. Because like Rigel and Betelgeuse are, well, one's a supergiant. Well, actually, they're both supergiant. One's a giant, and the other one's a supergiant.
Yeah.
So yeah, they're intrinsically very bright and apparently very bright. So they're fairly close by.
I used to know the distance to Betelgeuse off the top of my head. I want to say it was around 40 light years. Although I'm talking to a bunch of astronomers at AAS, they're about to correct me.
And Lindsay's actually just showing us the first data that came out
nice.
for this program. So Lindsay, do you want to walk us through what people are seeing? Or do you mind?
Yeah, so you can see, I'm zooming in here. You can see there's a lot of different spectra, and they're kind of one on top of each another going down. It's blue at the top, and we're going down redder and redder as we go further down, and it's brighter in the red. So you can see spectra there. You can see parts where there's like more emission coming out. And this is on the blue arm. If I go over here, you'll see the red arm. And you can see there's like big, what do you call it? Absorption lines there. And this is going from, it's flipped because of the mirror. So I think we're going blue to red, going up. And you can see the different features there as well. So it looks across a large wavelength range, but there's just tons and tons of data. So it kind of stacks up all on top. And you're seeing this, you're seeing two sets of data because there are two IFU. You're seeing IFU1 on the left and IFU2 on the right on each of the cameras. And that's why there's
the two rows that you see. The two rows that you see per let's say column per IFU. What is that?
Yeah, I think it's the sorry, it's a little difficult to control the count thing. I think this is one ISU and this is the other, I believe.
Right. Okay. Yeah. So, and then you can see the trace, right? So you can see the stellar trace down. I guess, yeah, you're on the blue camera right now. So if you go down to the red portion to the bottom, then you can see the trace that starts to increase, and it increases in strength to the red, and then you can see some spatial extent to the trace as well. So presumably there's some larger atmosphere of the star, or it's off-gassing. These stars are off-gassing in some way, because there's measurable spatial extent here. If I'm looking at it right.
Yeah, I agree. It doesn't look just like a. It doesn't look like a point source.
Like a straight point source, yeah. So presumably these stars are special for some reason, and that's why they're affecting.
Yeah.
So for Betelgeuse's distance, I was off by an order of magnitude. It is 400 light years away. I just want to make sure I'm correcting that on the record.
We're well far away, but Sirius on the other hand.
Sirius is only 10. That's what threw me off. Sirius is only 10.
So this is a 13th magnitude object, and actually, I mean, for most astronomers that are AAS, you would say, why are you pointing an 8-meter class telescope at a 13th magnitude object? So even though 13th magnitude seems like super faint, that's something you can get with, maybe a really good backyard telescope. But the thing is that GHOST, we're taking spatially resolved spectroscopy. So we're taking, we're breaking it up into just spatial resolution elements and trying to extract as much flux from a fairly small point source as possible. And we're dispersing the light at R of 80,000. So this is like, meter per second kind of resolution. And so you need a lot of photons to be able to disperse all that light. So I think the faintest sources that are observed with GHOST are in the neighborhood of, like, Lindsay, what would you say, like 15th mag, 16th mag?
He's gone down to 18. You don't see a lot by eye in the individual spectra, as you might expect, but they are able to reduce it, and if you take enough data over a long enough time, get good data out of it.
Yeah, so I think some of the quasars, so the active black holes, I think you really just barely start to get the ability to target some of the brightest ones in the universe at 18th magnitude or so. And so I think that this was part of the science verification testing of GHOST, was to look at these types of objects and see if you can eke out some sort of signal. But if you can get some spectacular information on the velocity of the gas entering into the black hole and being expelled by the black hole. So I guess they were able to do that.
I can see similar things going for star formation as well.
Right. Yeah.
Getting that level of detail around, a massive star.
Yeah. So the surface gravity, that's really helpful to get the dynamics of the atmosphere, and then any outflows that are occurring to get information on that. I don't know. So we were just taking a Gemini South observation prior of a tidal disruption event. So this is a black hole. Likely a black hole ripping apart a star, so that the tidal forces were ripping apart a star, and so that was what's called a target of opportunity, or a transient phenomenon. So something that happens once for a particular source and then likely doesn't happen again. And so they're pretty bright. I mean, they're intrinsically super bright, but they're usually far away. This was in another galaxy, and so that was kind of intermediate brightness for us. That was probably around 18th, 19th magnitude. These are sources that we could see pretty quickly, in a GMOS image in 5 seconds or something like that. And we can target it up and put a slit on it. But we go all the way to 26th magnitude. So the dynamic range, actually, I'm setting up some observations here on one of our instruments, GENIRS, that are of a negative magnitude object. And it's because we can look in the mid-infrared. The sky is super bright in the mid-infrared, so you need a super bright source to do this. So I'm setting up some observations that are minus 0.5 magnitudes, all the way to like 2 to 3 magnitudes, and then all the way to 26 magnitudes. So our dynamic range is like 10 billion, something like that, in terms of the brightness of sources. So it's kind of crazy, and all these sources go together on a single night. So we would point to something that's, you know, as bright, almost as bright as the brightest thing in the sky, Sirius. It's Sirius, right?
Star, yeah.
Yeah.
Unless you're going planets, but
Yeah. You were supposed to say
Oh, it only makes sense if people also know the name in Hawaii. Yeah.
It's almost as bright as the brightest thing in the sky to like some of the faintest galaxies that we've ever detected from the ground. So that all goes together on a single night.
Which one of the things that we were showing earlier is how all of the instruments of our telescope are all situated on the back of the telescope. This is true for Gemini North as well as Gemini South, although we have somewhat slightly different instruments on the two twins. However, being able to change between the instruments very quickly over the course of an evening means that there's a lot of advantage in being able to do a big variety of astronomical projects over the course of an evening and respond to time domain events where we're getting an alert that something's happening in the universe right now and we should switch over to looking at it. And that's a big advantage that Gemini has. Speaking of, I've been waiting to say this joke for a long time, which is that while we're observing on Gemini South, the GHOST instrument is not on Gemini North. It's only on the Gemini South. And we've been seeing a lot of great things that GHOST has been able to do. So always remember that Gemini South is the host with the ghost. Thank you for laughing.
That concludes our session. Hello, welcome in.
Yeah, we got another scientist walking in with us.
Actually, this is a GHOST principal investigator. So we're taking ghost observations right now.
Which program?
I can't say it on air here, Emma. No, it's FT113.
Okay.
So we have Emma Farina, who's joining us here.
Hi, everyone.
He's our acting head of science operations today at Gemini North. So he made the call to say we're gonna brave the snow tonight.
Yep.
He's our Q coordinator, so he spent all day. You can see how disheveled he is, all day making all the plans.
This morning I didn't have the beard. It just grew up. That's what happens.
And he's also an expert on high redshift quasars, and he also took the first ever ghost data of high redshift quasars. Is that right?
Yes.
Yeah.
So, yeah.
And what did you do with ghosts?
I took data.
And what did you
What?
And why did you take data?
So I don't know how much familiar are you with the high redshift quasars. So quasars are supermassive black holes that happen to be active. That means that there is a lot of like gas, dust, things that fall into the black hole, and this gas moves so quickly that they actually heat up so much that it starts to like bright like an old style light bulb. These are actually like is like a lot of light bulbs together, so you can observe them basically at any cosmic time. So from the Big Bang or just after the Big Bang to now. That's actually really helpful because there are not that many of such objects that have been observed from the ground, even if with an 8-meter telescope. So the fact that these objects are so bright is actually like helping us a lot to understand what's happened at the beginning of the universe. Specifically for my program, the amazing thing of GHOST is actually like is an incredible instrument. It allows you to go like with the spectral resolution which means how good are you to separate different colors in the spectrum of an object. We can observe like this object that typically takes like several like tens of hours in like an handful of hours, which may sound like a little gain, but if I tell you that your car can make 3 times the mileage with the same amount of gas, you get excited. Yes. And the same way we got excited for these things, if an instrument can get 3 times faster, is actually incredible because instead of staring to a single object for 20 hours, we can do that in 6, 7. You can imagine that there is a huge difference. Yes.
Not allowed to say that on Shadow of the Scientist. Banned.
What am I not allowed to say?
It's
Nothing.
go on.
I don't know what.
It's 6, 7. It's a meme amongst middle schoolers right now,
Oh.
and younger. But yeah.
7, 8 miles. Yeah, I imagine. I feel that.
This morning you would have gotten it.
Yeah. There is a difference between me at 8 in the morning and me at 4 in the morning.
About at 6
Yeah.
or 7.
Stop here. So I'm leaving now.
No, can you tell us about the quasars?
What were you hoping to get out of the ghost data?
Complicated.
Yeah.
But one of the cool things you can do is that is actually every single pocket of gas in the universe can cast sort of a shadow in the spectrum of a background object. So let's say that in a specific color range. So you basically try to see how much shadow or more like blocked light is in the spectrum. And if you imagine that every single pocket of gas is actually likely associated to either a galaxy or some filament of gas that connect galaxies, you can actually, it's the only way you can actually prove this kind of properties, because if you try just to stare to them, when I said 6, 7 hours, it means like 600 hours of observation, you may have something, so it's not really feasible. So that's the power. You have something really bright in the background, you have something in front that casts a shadow, and that doesn't depend how bright is the object is casting the shadow. It just, there is something that blocks the light there. And so you can start to do statistics on this kind of object and say, okay, how many I see them, how many, that's if every one of them is associated to a galaxy, I can count galaxies in counting how many shadows I see of those. If they imagine that, like if I have a gigantic galaxy much, much bigger than everything else, I have a bigger shadow. So if I see like bigger dark points in my spectrum, I can say, oh, this is a bigger galaxy, even if I don't see it. So this is what we are trying to see. There is other things that is like more complicated to explain. I don't think I have the mental status to say that. But
the idea was you wanted really high resolution spectroscopy that you could pick up these like very low mass systems in the way, right? Because what you're talking about is intergalactic medium tomography from the Lyman alpha line.
Yeah, that sounds cooler the way you said it, huh?
Yeah. So the quasar shines, and then some light is subtracted at different velocities as the light travels in between the quasar and us, right? And so they're just detritus in the way. There's just stuff in the way, and so normally we can't see that stuff. It's like we're looking out past the Milky Way. We always have to take into account the fact that we're looking through the Milky Way. There's stuff in the way, and so we have to make corrections to the data. But this is the data, right? So these blobs in the foreground are the thing you're looking for. You never see it without this really bright source in the
Exactly.
And so having this really high resolution, like normally we would take spectral observations that were hundreds of times less result than this, and so you'd only pick up the most massive gas clouds, right? But here you're able to pick up like even really small gas clouds in theory, right?
Yeah, that's cool. Thank you for explaining my science.
Wait,
I didn't know if I was taking a shot in the dark here, so.
We have a question from the Shadow of the Scientist crew.
Yeah, please. Oh, you're
D'Amico,
muted.
we can't hear you. It's funny because
You're still muted.
the Zoom is not saying muted, but I can't hear anything from you. Is our sound muted?
No, that's good. Yeah. You guys can put it in the chat if you want.
That might be fastest.
Like that. Okay, can you hear me now?
Oh, yep, we can totally hear you now. Yep.
apologize. We had to use a speaker from one of the great staff here at the Arizona Science Center.
Oh, awesome. Okay.
Yes, yes. And I wanted to apologize to those of you joining us virtually for not answering your questions in the chat. A very lively audience here in person. And so I've been answering questions and talking to people. So I apologize for that. So I'd like to go back to the top. Yes, the Hilo Memphis Stargazers, thank you so much for joining us. And yes, aloha. And then from Peggy Lameau, question. The question is, do you think that in any of these entities that you're viewing from there is a shadow of the scientist program looking at us? Maybe from their end. What do you all think, Emma, Brian, and welcome, Emma?
100% yes. It's probably have a different name. I don't know if another place in the universe they use English and they call it shadow scientists. They would be there. But I mean, as we observe every
FEMA arena. That's
that's the other one. Yeah. Arena Fa.
Well, I would hope so. I hope so too, Emma. Thank you.
They're probably looking at Jupiter, though, if we're being honest.
Maybe,
They're probably looking at Jupiter.
Maybe,
Yeah.
because it is quite bigger.
I have a story that I think is funny that relates to this.
Yeah, do it.
Whenever you look at a picture of a galaxy, we don't have a picture of our Milky Way that looks like any other pictures of galaxies because we're stuck inside the Milky Way. We don't get to look at it from that bird's eye view. And years ago, when I was working in a science center in a planetarium, we had an event where it was like we were thanking all the members for giving us money. And so I put up this nice, pretty picture of the galaxy M51 on the planetarium. And I was looking at this M51 galaxy on the planetarium, and I was looking up at it, and I was thinking, you know what? Any aliens living inside M51 would not have a picture of their galaxy because they'd have the same issue because they're stuck inside of it. They don't get a chance to take a picture of it. Yet I'm sitting here using it as a pretty picture in this program where people hopefully give us money at the end of it. I wonder if there's any aliens inside of M51 who are using a picture of the Milky Way in their planetariums in order to have other people give them money in the same way.
Probably like alien money. Though.
Yeah, alien money. And we'll never know. We'll never be able to trade back and forth of these beautiful pictures that we have.
That's a really fun thought. Everyone here was laughing at that because what a perspective to think about. Thank you for sharing that, Emily. And let's see. So we had a few more comments here. Let me get to those. I know we're at 1 minute left, so we can get these really quickly. Are there any unique targets for Gemini North or South that you all will be observing in 2026? And I know everything is Q observing, but do you have an idea if there are any unique targets?
Yeah, so we're already observing. So we break it up into 2 semesters. The A and B semesters, so 6 months each. We're already starting our 26A semester, so that it officially starts in the beginning of February, but we are already taking observations. And in fact, the first observations from the 26A semester were Emma. So I get to put the spotlight back on quasars and back on Emma. He's using our new low resolution integral field unit for the GENIRS instrument, which Emma and I are co-instrument scientists for. So we'll also put the spotlight on GENIRS. What's that program all about?
Do you know when before I say there is things you cannot see unless there is something in a black ground that blah blah the shadow? Yeah, I lied a little bit. And thanks, Brian, to put me on the spot and make sure that I embrace myself with this. So actually,
You need no help from me.
You're welcome. So actually, if you integrate for a long time with a really good instrument like GENIRS, you can actually start to detect a little bit of this light, this fuzz that is around those bright objects. And the idea is that, again, I like quasars because they're bright, but you can imagine that the quasar itself acts as a flashlight. So you don't only, it's like if you put a flashlight in the fog, you actually are able to see the fog much better than we are without the fog. So that's a sort of an idea. All the galaxies are surrounded by this large amount of gas that technically is like so dim that you will not be able to see it directly. unless you have a quasar in the center, this active AGN, active supermassive black hole, that is like shooting out like thousands and thousands of photons that actually illuminate the gas around that, and that make it brighter. And so hopefully we're able to see it. But I let you know, I just got the data, need a little time to process them, but I will let you know.
We just took it last week, right?
Yes.
Yeah.
And I was on holiday until Sunday, so it's.
But one other thing that I'll mention, thanks so much for that. A little bit closer by is so probably most people there have heard of 3i Atlas. So this is the third interstellar object that we know about that's coming to the solar system. It's now past its closest point, rendezvous point with Earth, and it's exiting the solar system slowly. But we have a number of new all sky surveys, so observations that are being taken every night of huge swaths of the sky. The biggest one being the Rubin, what's called LSST, Large Survey of Space and Time. I forget how they
synoptic survey, but then
it was Large Synoptic Survey Telescope.
Oh, okay.
Yeah.
Then they gave up on synoptic.
But so they image the whole southern portion of the sky every three nights. So over and over again, and super quickly. And so we didn't have this kind of capability. It's an 8.4 meter telescope, so it's a huge telescope doing this. It's really deep, really fast. That means you can see fainter things. There's a lot more fainter things than there are brighter things. So we have programs waiting for 4i right now. And who knows where it's going to appear? Is it going to appear in the south? Is it going to appear in the north? 3i we were able to see, and it came in a certain way. We were able to see from both the north and the south. So both, I think we got on 3i maybe 36 hours after discovery, and both the north and the south got on target about 20 minutes offset from one another. So we were able to observe with both telescopes at the same time. But so as soon as an alert goes out, it was 36 hours after discovery, maybe 12 hours after like confirmation. And so these programs are sitting latent in our queue, and they will be activated by scientists who are listening to these alerts, either in the north or the south, when that first observation comes in that hints at something like this. So that's definitely something to pay attention to this upcoming.
It's pretty amazing, but if it happens, it's not that great for me, because it means that they need to I spend the entire day to preparing what to observe tonight. And then someone say, well, at midnight, I want a telescope for myself. And so I have to change everything that I prepared during the day as quick as possible. Yeah.
So 3i was actually discovered on July 3rd. And I was down with my family on the Bayfront in Hilo, watching July 4th fireworks, setting up the observations. I'm contact scientist for all the 3i programs. So I was setting up all the observations for us to take that night on the north and the south, and then calling Chile and calling into here in the control room. So yeah, it's quite the event when it actually happens.
Well, you can see that in two ways. I would then let you speak.
Well, I was just gonna shout out everyone at AAS. If you want to learn more about Rubin Telescope, large telescope surveys, as well as the programs at Gemini North and South, make sure that you check out the NORLab booth at AAS, because they'll have a lot of information about all the stuff that we do.
Nice.
Awesome. We will definitely do that. And in fact, we went to the Rubin Observatory experience last night.
That was so amazing.
It was amazing, right? It was so amazing. It was incredible to see.
I sent pictures to my kids. And
Yes.
They were blown away by the
Yes, blown away by the pictures. Sorry, we're having side conversations
Yeah.
over here. Yes, but Emily, we will definitely do that. We will definitely do that. And thank you all so much for staying. I know we're slightly over. If it's okay, Emily, Brian, Emma, I'd like to get to one more question here, which was what are the logistical advantages of the observatory being in Chile?
So Jamaica, we're not in a huge hurry here, and actually, I think Lindsay could tell me if I'm wrong, but I think they'll be slewing again in like less than 5 minutes. So we could maybe end the session on a slew just to show how that works. If everybody's happy to stay.
That would be fun. I'm trying to figure out what we'll be slewing to.
Okay,
Because
sounds
the
good.
scene has increased to IQ 85, which I'm not super
Okay,
happy about.
okay.
But it is what it is. I'm trying to change the plan.
Yeah, so what Lindsay was saying is that the seeing is degrading a bit. So it was amazing seeing earlier. So we were getting like 0.6 arc-second seeing. Unfortunately, I talked about it, so I jinxed it. It blew up a little bit. So it's now. I mean, for most observatories, it would still be amazing seeing, but it's it's probably like 0.8 or 0.85, something like that.
Yeah, we're saying,
Yeah, 0.8,
yeah,
yeah.
about 0.8.
So not terrible, but not the like best of the best. Right. So the question was about logistical advantages. Yeah. So both sites, both Mauna Kea and Cerro Pachón, are dry, which is really important. We do observe in the infrared and the mid-infrared. Water vapor is a killer there. So having a sky that is dry is really helpful because it doesn't blind you. We're 7 hours offset, or right now we're 7 hours offset. So when it's nighttime in Chile, it's still daytime here. And so if something goes bump in the night, this difference in time actually helps us. Is it happening during our day and their night, or our night and their day? So
or in the 6 hours we cannot observe.
Yeah. But we can, yeah, we're basically 6 hours away from getting astronomical photons at maximum at all times. And it's in the south relative to the north. So we can both see equatorial targets, meaning so we can see the ecliptics of the plane of the solar system. We can see the celestial equator, so representation of our equator out onto the celestial grid. They're at 20 degrees south, roughly, latitude. We're at 20 degrees north. And so we are mirrored in that sense. And so they can still see all the way to like minus 90 declination, so all the way the full portion of the southern sky. But we got a lot of overlap. So we can train on the same target. We can use our different instrumentation suite in different ways. So it's a mirror, a copy, a sibling, but not really. So that's helpful.
Like Gemini.
Yeah,
twins.
exactly. Yeah.
Brilliant. Perfect. Thank you so much. Yes, thank you so much. Yes, Peggy. Thank you so much for an interesting evening. Yes, thank you for joining us. Thank you so much for joining us, Ms. Peggy. And we have another question here. This is from Ambrose. Commend the organizers of this webinar. Oh, what's that?
He's in Nigeria.
Yes, he's in Nigeria. I'm sorry, we're having side conversations with the group here. Estelle is saying, yes, Ambrose is joining us from Nigeria. And Ambrose says, this is my first time participating in this program. While I don't understand all the techniques involved in observations using the Gemini telescope, is there a template of step-by-step approach on how to access observed archived data and do data reduction and analysis?
Yeah, so the archive, I don't know, we don't have any videos for the archive, do we? I don't think so. No. That would be a great thing to make. Yeah, so we have a Gemini archive, and actually one of the really amazing things is as soon as the data is taken, within 30 seconds, it's ingested into the archive, and all the information. For example, some of the things that Lindsay was saying. So the seeing information, or where you're pointing in the sky, or how much, like if there were clouds, or like everything, like all of these sensors that we have, because we're observing remotely. So we have tons of sensors. And so all these sensors are piping back information about the temperatures of various things and everything. That's all encoded into the files.
Came back down again. So I'm going to stick to the IQ70 plan. Let's go to Q1088.
Okay.
So that's ingested into the archive, and you can read that information. So we have a proprietary period for some programs. So it means a group proposes for an observation, and the longest they can kind of hold that to themselves is 12 months. After 12 months, it's completely public domain. And a lot of programs eschew that proprietary period. So they say, we only need 6 months, or we don't need any time at all. So a lot of our programs actually are fully open access. And our telescope is also open access. So anybody in the world can apply. That's fairly unique among telescopes this large. So you can apply for time, and then we have tutorials on how to do that. The Gemini website, so www.gemini.edu, has tons of information on it. Almost some would say too much information, but we have tutorials. We have video tutorials on like how to set up observations or how to apply. The archive is a little bit more difficult to use, but you can put in the like target, like look, yeah, from the thing. So you can put in the target location. So like let's say you're interested in some star in the sky, you can just put in the right ascension declination, and then it'll come back with every single observation that we've taken there. And then you can download the data really easily. There's just a download button. And then you can use, we have a software called Dragons that can reduce a lot of the archival data. So this is a Python-based, hey, how's it? It's Python-based code, and it has tons of tutorials, and the installation is fairly easy, and running it out of the box is fairly easy as well.
Can I add two things? One, that you don't need to add array and deck. If you know the name of your target, you can even add the name of your target. So let's say you don't need to know where Jupiter is in the sky. You can just type Jupiter in every single observation we took with. So we try to be as open access as possible. And the second thing, that there is an effort to actually make the user or everyone in the world not to reduce the data, because this is a tedious task. And so a lot of observations are actually automatically reduced and uploaded in archive. So the idea is that you lower the threshold that you need to know to have access to actually the final reduced data set. Yeah. Mm-hmm. And so eventually in the future, everything will be reduced, everything will be ready, everything will be beautiful. At the moment, only some programs and only some instruments are in that stage. But for instance, GOST, the one I was showing there, is one of the best example where after a few weeks, you can just wait. You can reduce your own data if you want. You want to be sure everything there. But if you just want to click and download the data reduced, you just wait a couple of weeks. You click download, you get everything done.
And that's available to the public as well. So once the proprietary period is finished, you can download those data. I will warn. So a lot of observatories are moving to this. It's a really important priority. It's an important, as a community, we've prioritized this over the last 5 years or 10 years or so. And like Keck, they have their Keck Observatory archive, and they have Pipet is the software that they use to reduce a lot of the data. And they present that data on the archive for people to download. But there's a lot of subtleties associated with reducing data and the calibration association and trying to get the best possible information, especially if you're looking for really faint sources, or you're taking observations over multiple nights, or you're trying to combine observations from previous observations that have been taken 3 years ago. So if you really want to have the best possible data quality, as Emma said, you would want to download the data, reduce it yourself. And that is possible with this Dragons package, or Pipet is another really powerful reduction tool that's Python-based that doesn't take a huge amount of knowledge to reduce the data. And there's lots of tutorials and documentation associated. So hopefully that helps.
Yeah.
And thanks for joining us from Nigeria.
I shared the link to the archive in the chat, but as you guys mentioned, it can be a bit overwhelming to look at and navigate sometimes. Yeah. I'm not sure if there's a link to Dragons or anything we can share with that.
Yeah, I can. Yeah, and also we have a help desk. So we are really trying to be helpful here at Gemini. We have a help desk. You can go online. It's off of our Gemini website, and you can put in a query for the help desk. And we have a huge web of people, including myself, all the staff scientists, our national Gemini offices. So we have people all over the world that interface with our observatory and are really eager to answer questions.
Yeah.
Yes, you all. I just had a student walk up here. This is Tate, and wow, the camera just zoomed in on you, Tate. But Tate, would you like to share what you were just telling us?
As far as what do you mean?
Yeah, so you're observing with Keck, but this is your first time, your only real interactions with an observatory, really.
Mm-hmm. Yeah, so I'm a relatively young grad student, and my advisor submitted an application for Keck observing time. And now we're going in, I can't remember the exact date, but early February, to Keck to observe a binary AGN, which I'm super excited about.
What instrument are you using?
Yeah.
What's that?
Which instrument are you using?
What instrument are you using?
I wish I knew that off the top of my head.
Binary AGN.
Yeah, do you know if it's in the optical or in the infrared?
Infrared.
Infrared. I don't know what it would be.
Morse,
Osiris,
maybe?
Maybe Osiris or
Osiris.
Yeah, I think that's correct. Yeah.
Okay, yeah. So
Sounds
that's
right.
an infrared integral field unit spectrograph on Keck. I actually was just observing on Keck like a week and a half ago, and I was using KCWI, which is a optical integral field unit spectrograph. It was my first time ever using. I've been using Keck for like 22 years, but it was my first time using KCWI. It was awesome. It was so cool. And Osiris I've used many times. It's also really cool. They have a lot of spiffy software over there where it's just kind of point and click because they have a very different model, right? You just show up and you do the observations as a guest PI, and they have to have an interface that if you know nothing, you can just point and click.
Oh, yes, yes. Well, that's Tate. Will you be in person at Keck?
Yeah, that's the plan.
Oh, well, feel free to come down and visit Gemini.
Yeah.
We would be happy
Okay,
to
yeah,
stay around here.
We'll talk to my advisor and try to make that happen.
All right, awesome.
Yeah, we're just down the road.
Yeah.
Okay.
An hour away in another city, but down the road.
Just down the road.
I was depending
It's literally
which,
down.
Which
It's down.
part are you talking about? The front facility is down the road. The base
Yes.
facility is another city, but the base facility is easier to visit somehow.
Yeah.
I'd like to thank all of you for being in person here with me. Thank you, thank you, thank you. You made it so amazing. I'd like to thank our virtual audience as well. Of course, Lindsay and Pablo, we are grateful for the opportunity to shadow you. Thank you for allowing us virtually into the Gemini South control room. And as always, Emily, Brian, and our guest star here, Emma, thank you so much for being our amazing science host and guiding us through this special experience in our first session for 2026.